I now call to order the Society's 2,461st meeting in what is now the 151st year since its founding on March 13th, 1871. Good evening, everyone. My name is Larry Milstein. I am president of PSW, one of the oldest scientific societies of Washington, D.C., committed to providing a forum to further scientific understanding and inquiry. Welcome to our members, guests, and friends to tonight's lecture by Shobita Satyapal. I'm delighted that today's meeting is being held in person at the Cosmos Club, including a pre-lecture reception and dinner with our speaker. We plan to meet in person regularly going forward and to use Zoom and other social media when it's advantageous in the future as well. So please check the website often for up-to-date information. The Society is grateful to the sponsors of the 2021-2022 lecture series for their support, the Policy Studies Organization in cooperation with the American Public University, and a generous donor who asked to remain anonymous. We are also grateful to the sponsor of tonight's lecture, Jim Trefel, who's in the front row here. Thank you, Jim, who's pictured here with some of the 50 books he's written. I am pleased to announce the following new members: Kenneth Cowgill, a retired lawyer, formerly Assistant U.S. Attorney for the District of Columbia, interested in physics, astronomy, and epidemiology, despite his tenure as a lawyer, who learned a PSW from PSW member Dan Sisson. And tonight's speaker, Shobita Satyapal, who learned a PSW from our invitation to her to speak tonight, and whose interests will be clear in some small part from tonight's lecture. And we welcome them all to membership. If you're not a member and would like to join PSW or support the Society, you can do so through the PSW website using the blue Join button on the upper right-hand corner of the home page. We welcome new members and we appreciate donations. Recording Secretary James Heeland will now read the minutes of the 2,460th meeting and the lecture by Charles DeHaan on quantum information science and the National Quantum Information Sciences Initiative. James.
Thank you, Larry. Good evening, everyone. It's good to see you all. On June 3rd, 2022, in the Powell Auditorium at the Cosmos Club in Washington, D.C., President Larry Milstein called the 2,460th meeting of the Society to order at 8:03 p.m. Eastern Daylight Time. He welcomed new members, and I, the recording secretary, read the minutes of the previous meeting. President Milstein then introduced the speaker for the evening, Charles DeHaan, Assistant Director for Quantum Information Science and Director of the National Quantum Coordination Office, the White House Office of Science and Technology Policy. His lecture was titled, Quantum Information Science and Quantum Computing, the National Initiative. DeHaan said quantum mechanics enabled the physical construction of modern computing and communication. But until recently, computers operated on systems incapable of efficiently simulating quantum mechanics. In recent years, quantum mechanic research has evolved into information science. DeHaan said quantum information science is a foundational shift in information technology which will have unpredictable impacts on myriad fields. For example, he said quantum computers will factor very large numbers to render current encryption technologies useless. Building such powerful computers will require significant investment in technology-related fields such as quantum physics, microelectronics, and electrical engineering. The speaker then explained the basic science of quantum computing. A quantum bit, or qubit, is a two-level atom in its lowest state, which can quantum mechanically be in the superposition of both 0 and 1 at the same time. But when measured, a qubit is read only as 0 or 1 at any time. As qubits are added together, their system size grows exponentially. For that reason, quantum computing that relies on qubits is enormously more powerful than classical computing that relies on regular bits. DeHaan then described the many different potential realizations for constructing an actual quantum computer. He focused on superconducting circuits and electrons, two potential realizations that he said are analogous to modern-day fabrication of computer chips. DeHaan said current quantum computing error rates are 10 to 12 orders of magnitude difference away from being able to perform what he called useful calculations. DeHaan focuses his work on solid-state qubits. He prefers spin qubits, which are the most analogous to transistors in modern computers. They are simple, move quickly, and are compact. Within the spin qubit category are qubits with different spins. Certain multiple qubits may also be combined to form molecular qubits, which are extremely powerful but difficult to read. DeHaan then described the modulated readout approach his team developed with collaborators from the University of Wisconsin. Current large technology companies like Amazon and Google are using superconducting qubits to build quantum computers. DeHaan described these qubits as, quote, just wires on a chip, which are now as small as 20 nanometers across and superconduct at extremely low temperatures. He then described Google's recent quantum computing accomplishments and expressed optimism for future research into combining the best features of superconducting and semiconducting qubits. In response to the National Quantum Initiative, the Laboratory for Physical Sciences, or LPS, established the LPS Qubit Collaboratory to pursue disruptive fundamental research, build a quantum workforce, and grow collaborative partnerships to tackle the difficult problems in quantum research. Rather than ask for proposals to then fund, the collaboratory presents problems and invites collaborators to join in the work. One of the collaboratory's principal goals is to develop quantum qubit chips in the same way standard chips are currently manufactured. DeHaan described how the collaboratory reduced the problem into an approachable one, and the advances so far. The National Quantum Initiative Act was signed into law in 2018 and created 13 new centers across the country and established a committee to coordinate multiple bodies in pursuing quantum research and development. DeHaan said the three principal aims of the current U.S. administration are to get the science right, enhance American competitiveness, and build a workforce to develop a new quantum field of work. He then described current policy efforts to achieve those ends. The speaker then answered questions from the in-person and online viewing audience. One member asked whether the software or hardware were the immediate obstacles to further quantum research. The speaker said hardware is currently the biggest obstacle, but that he believes one of the approaches he presented will in fact work. A guest asked why the speaker's team used germanium instead of materials more commonly used in superconductors. The speaker said that holes in germanium structure avoid the indirect band gap issue presented in silicon quantum computing. After the question and answer period, President Milstein thanked the speaker, made the usual housekeeping announcements, and invited guests to join the society. President Milstein adjourned the meeting at 10:02 p.m. The temperature in Washington, D.C. was 24.5 Celsius. The weather was mostly sunny, and the number of in-person and live viewers, the number of in-person and live online viewers was 109, and the number of views on the PSW Science YouTube and Vimeo channels in the first 2 weeks, 433. Respectfully submitted, James Heelan, Recording Secretary.
Thank you, James. Online members can submit comments to Corresponding Secretary Robin Taylor at correspondingsec@pswscience.org. Not hearing any comments or suggestions about the minutes, or corrections even, I will entertain a motion from a member to approve the minutes as read. Do I have a second from a member? All members in favor? All members opposed? Hearing no opposition, the minutes are accepted unanimously as read and will be posted to the website in due course. We now turn to tonight's speaker, Shobita Satyapal, and her lecture on supermassive black holes. Shobita is professor of physics and astronomy at George Mason University, where she leads the Black Hole Galaxy Connection Group. Before joining the faculty at GMU, she was an instrument scientist for the James Webb Telescope at NASA Goddard Space Flight Center and at the Space Telescope Science Institute. Previously, she was a postdoctoral researcher at the National Air and Space Museum and NASA Goddard Space Flight Center. Her research centers on understanding the connection between the growth and evolution of supermassive black holes and the host galaxies in which they reside. She utilizes space and ground-based multi-wavelength data from a variety of ground and space-based observatories, including NASA's Chandra X-ray Observatory, ESA's X-Explorer, WISE, the Spitzer Telescope, formerly the Space Infrared Telescope Facility, the Very Large Array of the National Radio Astronomy Network, the Gemini telescopes, the Large Binocular Telescope, and the Keck telescopes. She's looking forward to using data from the James Webb Telescope after it becomes fully operational this summer. She is an author on numerous publications on her research. Among other honors and awards, she's the recipient of a NASA Presidential Early Career Award. She earned a BS in physics from Bryn Mawr and a PhD in physics and astronomy from the University of Rochester. Shobita, the stage is yours.
Okay, so thank you, Larry, for that very kind introduction. And thank you, Jim, for sponsoring this lecture. And thanks to the organizers for inviting me today to talk about a subject that's very dear to my heart, which is supermassive black holes, arguably one of the most enigmatic objects in the universe that lurk in the centers of galaxies. So as I was reflecting on giving this talk at this very historical club, I looked back to where we were in 1878. And I pulled up this picture of Pennsylvania Avenue. And it's indeed quite remarkable how far we've come. At the time, Einstein wasn't even born. And it was yet to be 40 years before he formulated the theory of gravity. And Karl Schwarzschild soon afterwards, who was the person who proposed the mathematical solution to Einstein's equations, which laid the foundation for what we know about black holes, had only done that a year later, actually while he was in active duty in World War I, which I actually recently learned that he actually solved Einstein's equations, while in active duty, in his musings on the side. Amazingly, we didn't even know that Pluto existed. It was 50 years before Pluto was discovered. And there were no galaxies that we didn't know that there were other galaxies at that point. And I was reflecting, actually, I went back and looked at the literature to see what was published at the time. And almost every article that I could find mentioned the sun or the inner planets. And there was a lot published about Mars. And I actually found this. And believe it or not, this is the front page of the New York Times in 1911. So we've come a long way from that time. And we are on the threshold of some very amazing discoveries in the cosmos with the launch of the James Webb Space Telescope. And I feel a deep gratitude to be able to participate in this field at this very amazing time. And I wanted to begin with this talk with a very familiar image. This is an image of the Hubble Deep Field. And the reason I chose to begin with this image is very soon, as Larry mentioned, the science operations will begin on the James Webb Space Telescope, and we will get the deepest view of the universe by July 12th, actually, when the press conference will take place. And so, as you know, many of you have seen this image time and time again, but I like to begin by just reflecting on what we know of the universe right now. So if you take a dime and you hold it out at arm's length, this is what you see when you stare with the Hubble Space Telescope for 11 days straight. It's 4 trillion times fainter than what the human eye can see. And in that tiny patch of sky, there are 10,000 galaxies, each one with several 100 billion stars, each one several 100,000 light years in extent. So we've come a long way since this club was first founded. And yet I reflect on how little we actually do know. Fundamental questions are still unanswered. How did these galaxies form? Why did they form this particular way? They come in many different shapes and sizes. And of course, what is their ultimate fate? And so these are fundamental questions in extragalactic astronomy that we have yet to answer. So I want to begin my story about supermassive black holes with the story of what lies in the center of the Milky Way. And many of you are familiar. This is our Milky Way. It's roughly 100,000 light years in extent, about 1,000 light years in thickness. And we're somewhere in the disk of this galaxy, orbiting around the center, roughly 26,000 light years from the center of the Milky Way. And we're moving at tremendous speeds, about 230 kilometers per second. That's about 125 miles per second. So I could get to New York City in 2 seconds at that speed. And so we're somewhere on that disk, as I said, 26,000 light years out, moving at that speed. And for a long time, we didn't know what was at the center of the galaxy. And that's because we reside in the disk of the galaxy. And it turns out that the universe is actually very dusty. And so if you try to look at the center of the Milky Way in optical light, you actually can't see it. So it's just a dark, invisible to optical wavelength. And so you have to look in the infrared part of the electromagnetic spectrum. And this is, oops, uh-oh, how do I go back here? Okay, so this is an image from the Hubble Space Telescope, a very famous nebula that many of you have probably seen. This is an image in the optical part of the electromagnetic spectrum. And if you take the same picture in the infrared, you can see that you can see through the clouds of dust and gas. So in order to see the center of the Milky Way, you need to observe the universe in the infrared part of the electromagnetic spectrum. And this wasn't possible until roughly 25 years ago, or roughly 3 decades ago, when on the tops of mountains, people were able to peer into the center of the Milky Way by looking at infrared observations. And this is what they saw. And this is a very famous zoom in of the galactic center. And what they saw was amazing. So as you zoom in closer and closer to the center of the galaxy, all of a sudden, as you can see here, there's a dense cluster of stars. In fact, in the distance between us and the nearest star, in the center of the Milky Way, there are 10 million stars. So it's a very exotic place, unlike any other location in the galaxy. And what's more is that the stars are moving incredibly fast. So this is a zoom in. This is from the Max Planck group in Germany, and now the Keck group, led by Andrea Ghez, showing the orbits of stars around the center of the Milky Way. And they're moving incredibly fast. How fast? 10 million miles per hour, and roughly the size of a solar system. And when you measure those speeds in that size, you can derive the mass. And as many of you have known, the mass of this dark object at the center of the Milky Way is 4 million times the mass of the sun. And of course, you might have seen the recent press conference. We now have an image from the EHT collaboration showing the black hole shadow at the center of the Milky Way. And so there's irrefutable evidence for a supermassive black hole of mass 4 million times the mass of the sun residing in the center of our Milky Way. And of course, this won the Nobel Prize for the very nice work done by Andrea Ghez from UCLA and Reinhard Genzel's group in Max Planck Institute in Germany. And as you can see, there's irrefutable evidence for this supermassive black hole. And this revolutionized the field. What is this supermassive black hole doing in the center of the galaxy? How did it get there? How did it form? What impact does it have on the whole galaxy? And of course, how common are they? Well, it turns out that supermassive black holes don't just reside in the center of our own galaxy. You've all probably seen, in fact, you've had a speaker from the EHT collaboration at this very series, and you've seen the press images on the black hole shadow in the center of M87. And this is a zoom in from the Hubble Space Telescope all the way through the EHT image that I'm sure you've seen before, showing a much more higher and higher resolution image, ultimately to the black hole shadow. So you can see that supermassive black holes are not unique to our Milky Way. They're found in the nearby galaxy M87. And it turns out that that's just not the only two galaxies that have supermassive black holes. This is a zoom in. This is an actual real image taken with the Sloan Digital Sky Survey robotic telescope at Apache Point. And if you look at the centers, in the centers of all nearby massive galaxies, it turns out that there's evidence for supermassive black holes in every single one of them. So supermassive black holes appear to be fundamental components of galaxies. Not only are they ubiquitous in the universe, but they possibly represent fundamental components. Maybe they're the seeds from which galaxies form. And it turns out that the mass of the supermassive black hole, which can range from 1 million solar masses up to 70 billion times the mass of the sun, the mass of the black hole is tightly correlated with the mass of the galaxy in which it resides. So you can see here in this plot, plotted here is the stellar mass of the galaxy versus the black hole mass, and the bigger the black hole, the bigger the galaxy in which it resides. And that baffled astronomers. So that's a relatively recent discovery in the past couple of decades, which strongly suggests that the supermassive black hole somehow plays a role in shaping the evolution of the galaxy. And just to keep in mind, the Schwarzschild radius, which is the radius beyond which light can't escape, for the black hole in the center of our galaxy is 17 times the radius of the sun. That's tiny compared to the size scale of an entire galaxy. So 17 times the radius of the sun is roughly 2 light seconds. And just to give you a sense of scale, the nearest star is 4 light years away. And the size extent of the entire galaxy is 100,000 light years. So it's quite surprising that somehow the mass of the galaxy is linked to the mass of the supermassive black hole. So we think now that supermassive black holes somehow have an impact on the host galaxies in which they reside. And you can see here in this image that we now know that supermassive black holes don't just consume material. In fact, some people think of black holes as cosmic vacuum cleaners, but they actually expel material. So as you can see here in this image of a very famous active supermassive black hole, material can be ejected at relativistic speeds, and huge quantities of gas can be expelled. And the amount of mass that can be expelled can actually exceed the mass of an entire galaxy and be flung out into the intergalactic medium. We also know that galaxies can collide with each other, and galaxy collisions are quite frequent. So a typical galaxy has undergone 1 to 3 cosmic collisions with another galaxy in cosmic history. In fact, as many of you probably know, that the Milky Way will collide with the Andromeda galaxy. And we now think that as these collisions occur, gas is funneled towards the center of the potential well, where it can feed the supermassive black hole. And we know also that when black holes collide with each other, they give rise to gravitational waves. And so you've been familiar, and I think you've had someone speak here about the LIGO detections. And I'm just going to play a very quick movie just showing what happens when two black holes collide. And so you can see that they're moving at relativistic speeds until they come closer and closer. And boom, see the gravitational waves that traveled 1.3 billion miles, where they reached the LIGO detectors, and we heard the sound. And that was in 2015. So we know that black hole collisions occur, but these black hole collisions that were detected by LIGO did not detect supermassive black hole collisions. So this is just a schematic showing the detections from LIGO, and you can see that none of them extend to millions of solar masses, which is the mass range of supermassive black holes. And this is because the LIGO detectors are not sensitive to black hole collisions in this mass range. So I'm going to talk about supermassive black holes, and there are two big outstanding questions that I'm going to focus on today. So the first question is, how do supermassive black holes form? And the second question is, how do they grow to such tremendous sizes? And the answers that I'm going to focus on today, and this is the subject of the research that I do with my research group, is can be found in studying supermassive black holes in low mass galaxies in our neighborhood, and studying active accreting or feeding black holes in merging galaxies, or active galactic nuclei, or AGNs as they are often called. So these are the two areas that I want to talk about today. And the first question I want to focus on is how supermassive black holes form. So the theory behind typical black hole formation is very well understood. So we now know that massive stars end their evolution in a supernova, And if the stellar remnant is massive enough, then no force can prevent it from collapsing to a singularity, and a black hole is born. And so these are the black holes that have been found in our galaxy. The first one was found in 1964, I believe. And the theory is very well understood. They're simply the remnants from massive stars. So they're dying massive stars. But the theory behind supermassive black holes is still not well understood. How do you get a black hole that is 1 million times or 4 million times the mass of the sun to form? And this really has posed major theoretical problems to the astronomical community. And this has been made even more challenging by the discovery of quasars in the early universe, so at very large distances. So quasars are extremely active or feeding supermassive black holes that were discovered in the late 1950s and early 1960s using radio surveys and follow-up optical spectroscopy. And as we get bigger and bigger telescopes, we're finding quasars at greater and greater distances when the universe was young. So you can see here, this is just a rough timeline from the Big Bang to the present day. And you can see that the discovery of quasars, some with masses extending to 70 billion times the mass of the sun, being formed at very, very high redshift when the universe was only a few 100 million years old, pose significant challenges to the formation theories of supermassive black holes. How did you form them so early in the universe, and how did you grow them to such tremendous sizes? So that is an extremely active area of research. And what I show here is a plot of the mass of the supermassive black hole in units of the mass of the sun as a function of redshift. The higher redshift is the higher look-back time, so earlier in the universe. And you can see that at very high redshifts, there's a growing population of active supermassive black holes, or quasars. And even as we speak, there are more being discovered. In fact, I think there's going to be a new data point somewhere over here that I think will be announced soon. But you can see that there are over 200 supermassive black holes at very high redshift, some with masses up to 10 billion times the mass of the sun, and when the universe was really only a few 100 million years old. So, as I said before, this poses significant challenges to theories of supermassive black hole formation. And I wanted to give you just an overview of some of the theoretical ideas that people have put forward on their formation. So the first is simply the end products of the most massive stars in the early universe. So at some point, there was a first generation of stars, and those stars in the early universe are called population 3 stars. And we think that in the very early universe, when the universe consisted mostly of hydrogen and helium and trace amounts of lithium and beryllium, that stars could get much more massive. And those stars seem to be able to produce black holes on the order of 100 times the mass of the sun. So that's significantly larger than the mass of black holes that are found in our own galaxy. They're just a few times the mass of the sun. But we think that the conditions in the early universe would favor extremely massive stars and massive remnants that could get as massive as 100 times the mass of the sun. Now, unfortunately, what makes that difficult is that if you only had 100 solar mass star, somehow it would need to grow to 70 billion times the mass of the sun in a relatively short period of time. And that's because we're finding these quasars at very high redshifts with extremely high masses. The problem with that is that you can't grow a black hole at an arbitrarily fast rate. And that's because that as matter falls towards the center of the potential well, it radiates electromagnetic radiation. And radiation carries a pressure associated with it, radiation pressure, which counteracts the effect of gravity. And so there's a limit to how fast a supermassive black hole can grow. And that poses significant challenges to theories of supermassive black hole formation in the scenario of these population 3 seeds, supermassive black hole seeds. So they're easy to form because we know at some point in the universe started forming stars, but they're extremely hard to grow so early in the universe. Now, the other main theoretical idea is that perhaps in the early universe, the conditions could have been just right to form supermassive black holes directly from gas clouds. Now, theoretically, that's extremely difficult to do, to have a massive cloud in the middle of space just collapsing and forming a black hole. However, if you do indeed form such black holes, then you wouldn't have the same challenge in being able to grow it to such tremendous sizes in a relatively short period of time. And there are theories in between these two extremes where you could have black holes forming in stellar clusters and then merging to form a more massive black hole. So these are the different theoretical ideas that have been studied so far. And this schematic just emphasizes the difficulty of the problem. So here are the quasars. They have very massive black holes. You can see the black hole mass here. And then somewhere in the beginning, you could have stellar remnants in the very early universe. And the problem is they would have to grow extremely rapidly to get to this mass in the required time. Or alternatively, you could start with more massive seeds, which would require a less challenging method to grow to supermassive black holes in the required time. So that's sort of a summary of where things stand in the field. It's extremely challenging to explain the existence of supermassive black holes so early in the universe, when the universe is only a few 100 million years old. And so the bottom line is we really don't know. These are really one of the fundamental outstanding questions in the universe. Supermassive black holes exist, they're ubiquitous, they're found in the centers of galaxies, they're found at extremely high redshift with masses that are a billion times the mass of the sun, and we simply don't yet know how they form. So I think that's going to be one of the major breakthroughs that we will see in the coming decade. And so one of the difficulties is that we can't observe the original seeds of these supermassive black holes. They're just at too high redshift, and there are even challenges with the James Webb Space Telescope in detecting these very first supermassive black holes. And so what I'm going to talk about today is how we can use some constraints in the local universe to shed light on this question. And what I'm going to argue is that low-mass galaxies or dwarf galaxies in our local universe can tell the story of the formation of supermassive black holes in the high redshift, the unobservable high redshift. And the reason for this is the following, that if supermassive black hole seeds originated in the first generations of stars, they wouldn't have been very massive because the first generations of stars could only produce seeds on the order of 100 solar masses. but they would have been easy to form. And so if you look at dwarf galaxies, which have not undergone mergers or accretion events throughout cosmic history, then if population 3 seed formation is the most common method of black hole formation, then you would expect the low-mass dwarf galaxies to contain a significant fraction of low-mass black holes. So alternatively, if supermassive black holes formed from some exotic phenomena of gas clouds collapsing to massive black holes, since that's a harder thing to do, you would expect that they would be rarer. So what you can see here is the fraction of local dwarf galaxies, and in the horizontal axis, that's just a measure of the mass of the galaxy. And what you can see is that the two different theories predict a different occupation fraction of supermassive black holes as a function of stellar mass. So lower mass galaxies would produce a higher fraction of supermassive black holes. And what's seen over here is the black hole mass as a function of the mass of the galaxy. And you can see that both models predict different masses of supermassive black holes. So if supermassive black holes formed from the first generations of stars, then black holes should be common in low-mass dwarf galaxies, and their masses should be small. Alternatively, if supermassive black holes had their origin in this exotic phenomenon of primordial gas clouds, then you should find that supermassive black holes are rare in low-mass galaxies, and their masses are large. So basically what this says is that you can use local galaxies, for which we have telescopes that can observe them, in great detail, to tell the story of supermassive black hole origins. And so that's one of the active areas of research in this field, and one of the projects that my group is working on. And these black holes, should they exist, would be intermediate in mass, so not as massive as the supermassive black holes. And we call these intermediate mass black holes, or IMBHs. And the problem with that is that they're hard to find. And the reason they're hard to find is that because their masses are smaller than, for example, a 70 billion solar mass, they exert, it's more difficult to detect the gravitational influence that they exert on the surrounding stars and gas. And so the sphere of influence of the supermassive black hole, namely where the motions of stars and gas would be influenced by the black hole, is extremely small. In fact, if you look at some of the closest galaxies, the sphere of influence of these smaller mass or intermediate mass black holes is just like that little red dot. So the angular resolution of your telescope that you need is on the order of 1 milliarcsecond. So that's like, just to give you a sense of scale, that's like if I were to hold a quarter, it would be like someone in Paris trying to read the quarter. So it's extremely high spatial resolution that's required and is basically not feasible. So we can't detect intermediate mass black holes the way we have been measuring the masses of supermassive black holes, like the one around the center of the Milky Way and in roughly 100 nearby galaxies, where the mass of the black hole is big enough that you can actually resolve that sphere of influence. Once you get into the intermediate mass black hole regime, we simply don't have the angular resolution to actually measure its gravitational influence. And therefore, this has been an extremely challenging field. Even though the dwarf galaxies are nearby, we simply can't confirm whether there's an intermediate mass black hole at the center using these dynamical techniques to measure the gravitational influence of the black hole. And so as a result, we need to search for accreting supermassive black holes. And when you have a supermassive black hole, as you can see in this very nice animation there, matter falls towards the center of the potential well. And that loss in gravitational potential energy can be radiated across the electromagnetic spectrum. So the gas very close to the supermassive black hole is orbiting at relativistic speeds, with the gas moving faster the closer it is to the center of the potential well, closer to the black hole. And that matter rubs against each other, and through dynamical friction, radiates. It gets extremely hot. In fact, accretion disks, these are called accretion disks around supermassive black hole, get to be several tens of thousands of degrees Kelvin, so extremely hot, much hotter than the photospheres of even the most massive stars. And so these accretion disks radiate at very high energies, at X-rays and gamma rays, well above what's seen in the radiation from stars. And this is just to give you a sense of where the light is emitted from a population of stars, which you can see by this red line over here. And this is energy on the horizontal axis. And in blue here is the typical spectrum seen from an accreting black hole. And the key takeaway here is that you see radiation at very, very high energies. And that's why astronomers often use X-ray telescopes to identify accreting supermassive black holes in the centers of galaxies, simply because stars don't emit a significant fraction of their light at X-ray wavelengths. So if you detect a lot of X-ray radiation from a point-like object at the center of the galaxy, that is very robust evidence for an accreting supermassive black hole. Now, when you have very high energy radiation that is being emitted at the center of a galaxy, it can ionize the gas around it, and that gas can produce specific spectral signatures that uniquely identify the accreting supermassive black hole. And just to give you a sense, this is the spectrum, the optical spectrum that you see from a galaxy that does not have an actively accreting supermassive black hole. And you can see that it's not very remarkable. There are these absorption features in the spectrum. But this is what the optical spectrum of an accreting supermassive black hole looks like. And you can see it's dramatically different. So you have unique signatures here. You have extremely broadened lines. They're Doppler broadened from very fast moving gas around the center of the galaxy. And you have very clear emission lines in stark contrast to the spectrum I showed you earlier of a galaxy that does not have an accreting supermassive black hole. And so what we think is happening is that the accretion disk is emitting this very high energy radiation, which is ionizing the surrounding gas and producing this unique signature that identifies an accreting supermassive black hole. And so this is how astronomers have been looking for feeding supermassive black holes in the centers of galaxies. They take spectra, they see these unique signatures, and from these unique signatures, they can derive important properties and infer things like the mass of the supermassive black hole by looking at widths of spectral features. So that has been, quite a cottage industry where people are looking for accreting supermassive black holes in the centers of dwarf galaxies to see whether they exist and whether we can put any constraints on the mass of the supermassive black hole. And this is where I wanted to highlight some of the work that my group has been doing. This is Jenna Kan, a former PhD student who is now at NASA Goddard. And so what we decided to do is that we recognized that intermediate mass black holes, which remember are the things that we're looking for in the centers of dwarf galaxies because we want to put constraints on supermassive black hole origins, don't look like their more massive counterparts. And the reason for this is that as the black hole mass decreases, the size of the Schwarzschild radius of the black hole gets smaller. And because of that, the gas around the black hole gets hotter in smaller black holes. So smaller mass black holes should produce hotter accretion disks. And this is actually a model of what the temperature of the accretion disk looks like as a function of black hole mass and how fast it's feeding. And shown here is where the energy is emitted from black holes of different masses. And the key takeaway in this black line you see here, this is the least massive black hole and this is the most massive black hole. And the key takeaway is that more of the energy gets emitted at higher and higher energies or shorter wavelengths. So intermediate mass black holes that are accreting do not look like accreting supermassive black holes. And indeed, they should therefore show a distinctly different spectrum than accreting supermassive black holes. And unfortunately, most of the searches so far have been carried out using the traditional methods, and they haven't found very many intermediate mass black holes. In fact, if you look at candidate intermediate mass black holes, this is the largest mass black hole that has been detected by the LIGO detectors. And you can see that the next biggest black hole that's known in the universe is more than an order, 2 orders of magnitude greater than the LIGO detections. And there are very few of these lower mass black holes. In fact, the total number of black holes between the mass of the LIGO detection is really several orders of magnitude. So there's a big desert in the black hole mass regime that's missing. And this has been a topic of active research by my group and many other groups, is the hunt for this missing population. So if you really want to understand the origin of supermassive black holes, you really need to find this missing piece of the puzzle. It's almost like, you see a population of babies and you see a population of elderly people, but there's just nothing in between. And so we're on the hunt for this intermediate mass population. So armed with this knowledge that the accretion disk of these lower mass black holes are hotter and they should emit a unique and different signature, we conducted observations at the Keck telescope, and you can see Jenna here right at the summit of Keck, and the Gemini Observatory and the LBT, showing the spectral signature from 2 dwarf galaxies that we happened to get time to observe. And we saw clear evidence for an accreting intermediate mass black hole, just as our models predicted. And so these were invisible through previous techniques, and they were made possible through infrared observations from these great observatories. And so we were extremely excited by this discovery. And so we applied for observing time on the James Webb Space Telescope. And I feel great gratitude that we're given time to look at 2 particular dwarf galaxies. And this is just a plot showing the stellar mass of the population of dwarf galaxies that have been studied so far. And just to give you a sense that on the high end of this dwarf galaxy histogram is the Large Magellanic Cloud, which is a tiny irregular galaxy. This is our Milky Way. That is a close neighbor of the Milky Way. And that's over here. And one of our targets has a mass that's 3 orders of magnitude smaller. So we got time to look at one of the tiniest galaxies in the local universe to see if it has a supermassive, an intermediate mass black hole. And James Webb Space Telescope has the sensitivity to detect it, unlike any facility on the ground. So hopefully in the next year, we'll be able to tell you if we did detect the first intermediate mass black hole with a mass predicted to be about 1,000 times the mass of the sun. So we were extremely excited with that discovery. And so the next question that I want to focus on today is how do supermassive black holes grow? So as I told you, we now know that these supermassive black holes exist at very high redshift and that their masses extend up to 70 billion times the mass of the sun. And so an obvious question is, how during cosmic history do they grow to such tremendous sizes? And one of the main mechanisms by which we think supermassive black holes grow is through the merging of 2 galaxies. As shown here is a simulation of 2 galaxies that are merging. And as I mentioned before, these galaxy mergers are common in the universe. And you've probably seen some spectacular images from the Hubble Space Telescope of merging galaxies. And what happens is that as the 2 galaxies merge, you can see that the ordered rotation of the disk is disrupted, and gravitational torques cause gas to funnel towards the center of the potential well, where it can potentially feed the supermassive black hole. And simulations predict that you can actually get significant growth during this process. So this should be an efficient way by which supermassive black holes grow through cosmic history. So that's all well and good. Supermassive black holes we know are common. We know that galaxy collisions are common. We know that simulations predict that matter should fall towards the center of the potential well, where it can grow the supermassive black hole. So this should be a viable explanation for rapid supermassive black holes growth in cosmic history. And so it's been a very active area of research is to search for accreting supermassive black holes, active galactic nuclei or AGNs, in colliding galaxies. And unfortunately, what's been found has been surprising. AGNs in galaxy mergers are actually rare. So before I showed you images from the Sloan Digital Sky Survey, looking for those unique signatures of accreting supermassive black holes. Well, it turns out that only 1% of galaxies show those signatures. So they're indeed rare. Furthermore, simulations predict that as matter falls towards the center of the potential wells of the galaxies, both supermassive black holes should light up as active galactic nuclei. So you should see a large population of dual AGNs, or dual feeding black holes, in the centers of galaxies. But dual AGNs are actually rare. In fact, there are only on the order of 30 known in the entire universe. And so, again, we looked at possible explanations for this. And as I showed you before, the center of the Milky Way is very dusty. And so in galaxy mergers, as I mentioned, matter falls towards the center of the potential well. And that very matter can obscure the accreting supermassive black hole, preventing us from detecting its signatures in the optical part of the electromagnetic spectrum. And so many groups have been now looking in the X-ray part of the electromagnetic spectrum, which can allow you to see through the dust and gas, and infrared telescopes. And that's what we've been doing actively So we've been searching for AGNs using X-ray and infrared light. And our goal is to find them, determine their masses, and how fast they're feeding or their mass accretion rates. And we've been doing that with a slew of observatories, the WISE Infrared Sky Survey, the Chandra Space Telescope, the New Star Observatory, Keck, and the Large Binocular Telescope. So, and what we found is that if you look at galaxy mergers, and here's just an image of galaxy mergers from the Sloan Digital Sky Survey, you can see that there are spectacular examples of galaxy collisions or mergers in the universe. Here's some other more advanced mergers. And if you look for signs of accreting black holes in these centers as a function of the stage in the merger, so that's the separation between the two galaxy nuclei, which is shown on the horizontal axis. And if you look in the optical part of the electromagnetic spectrum, you see a modest increase in the fraction of galaxies that are actively accreting, just shown in the vertical axis. But then if you look in the infrared, which are the blue and red points, the red point over here actually, you can see that you see a tremendous increase in the fraction of galaxies that are accreting. So our work showed that accretion activity indeed is happening in galaxy mergers, but you can't detect it in the optical because of obscuration from the intervening material. So I wanted to highlight another program that we did. And I should say that in our field, we have to write proposals to convince a panel of peers that our scientific ideas are compelling. And I remember starting this, I think, 2014, so a long time ago. And at the time, people said, oh, no, there are no, we already know that there are no active galactic nuclei in these galaxy mergers because they don't show signatures in the optical. So I remember struggling and writing a proposal, and it was turned down. There are hundreds and hundreds of proposals that get submitted, and only a fraction get accepted. And so I remember I had pneumonia, and these telescope panels happen yearly. So this is for the Chandra Space Observatory, which is an X-ray telescope, a quarter of the way to the moon, and was the largest space observatory until recently. Every March you have to put in proposals, and I remember being extremely sick, and my research group said, "No, we got to do it," and we all pitched in and worked really hard and submitted a proposal, which unfortunately didn't get time. And so we did it again, and we asked to observe these galaxies over here, all of them merging, none of them showing signs of feeding black holes in their center in the optical part of the spectrum. And finally, we got the TAC to agree that, okay, let's give these guys a chance, and let's take a look at these objects. And this is what we found. So every one of those point sources is an X-ray source that can only be produced by an accreting supermassive black hole in the center of the galaxy, detected by the Chandra Space Observatory. After pneumonia and a lot of hours of work, we finally got what we were expecting. Doesn't always happen. And what's more is that 8 of the 15 that we got observations for actually showed 2 X-ray point sources indicative of dual accreting supermassive black holes. And so remember, I told you that there were only roughly 30 known, and this observing program on its own increased that number significantly. So there are 8 more now known, simply by looking in the X-ray part of the electromagnetic spectrum. And that generated a lot of press, which was a lot of fun. And it basically taught us a message that what you're looking for can often be right in front of your face, but you're simply not looking with the right set of eyes. And we really needed X-rays to look in the centers of these galaxies, or infrared telescopes, which we now have with the James Webb Space Telescope. So you can imagine what proposal I'm going to be writing soon for that observatory. Another thing that happened is that a former student of mine, Ryan Fifley, who's just graduated and is now at NASA Goddard as well, and he very keenly noticed that this particular object over here seems to have not just 2, but 3 X-ray point sources, which had never before been seen. And in fact, we then wrote proposals, desperately, with our collaborator. We called Barry Rothberg at the Large Binocular Telescope and said, you've got to take a spectrum of these 3 different objects. And we got our collaborators, Gabby Canaliso and her students, to do follow-up spectroscopy. And guess what? We confirmed the first triple accreting supermassive black hole in a galaxy merger. You can see there's evidence for extremely broad lines, which is a signature of an accreting black hole. And it's 1 billion light years away, this particular object. It has a mass of 500 million times the mass of the sun. And we also detected evidence for material that's being flung out of the galaxy at speeds of 1,500 miles per second. So that work we published a couple of years ago. And it actually made it to the New York Times, which was a lot of fun. And so that just gives you a flavor for some of the work that my research group has been doing. And a key takeaway that I wanted you to realize is that we really need telescopes that operate outside of the optical part of the electromagnetic spectrum. And you are all, I'm sure, anticipating, as I am, the results from the James Webb Space Telescope. And I really want to remark and show deep gratitude for the team that made this possible. It was indeed a real technical marvel to launch such a huge telescope in space, to fit it in a rocket, to have deployable optics operating at cryogenic temperatures. And this is JWST when it was on its way to its final orbit, which is where it is now. And I just wanted to tell you that be prepared to be amazed on July 12th. I'm sure you'll all be tuning in for the press release. And I'm sure you've seen this image, one of the early releases. As Larry mentioned, I did use the Spitzer Space Telescope. So on the left, you'll see an image of the Spitzer Space Telescope of a nebula. And this is an image with one of the instruments on the James Webb Space Telescope. So it's going to be spectacular. And I actually just want to leave you just want to introduce you to my group at George Mason University. So I have numerous students and the list keeps growing. Here's a sampling of some of the students that I have right now. They've been incredibly dedicated and it's been an absolute pleasure to work with them. And I wanted to just give you a sense for how much fun it's been to be an astrophysicist. My students have been to all kinds of exotic places and have had a lot of fun. This is on a whale watching tour when we were up in California. They've gone and presented their work. In fact, they're at a conference right now at the AAS meeting, which is in Pasadena right now. Some of them have a little bit too much fun. And they go and perform dangerous feats. And it's been an utter joy working with them and being able to work in this field. So thanks very much for your attention, and thanks to NASA for supporting this work. And leave you with this image, which I often show in public talks, emphasizing why we astronomers really want big telescopes. And we've got one. And so stay tuned for James Webb. Thanks for your attention.
We have time for questions. So we'll start with Frederica in the red microphone.
My name is Frederica Derima. I'm a member. Thank you very much for a very fascinating presentation and travel through the history and also what we can be looking in the future. I have a question that may be simple and follow up with my main question. How do we calculate the mass of the black holes and make these estimates? And my ultimate question is, you gave a model in the beginning of the large galaxies that they have larger black holes, and you talked about how in the center they move much faster. So the probability of collision and merging, what are the mechanisms to such mechanisms? And the other thing is it possible that there's another force that is manifested at these scales that we don't know about? Thank you.
Yes, so the first question I think you had was, how do you measure the mass? So as you saw for the galactic center, you actually measure the orbits of individual stars. But in external galaxies, and so far astronomers have done this for roughly 100 galaxies, they measure, they're able to resolve the sphere of influence, so where the black hole has a gravitational influence on the surrounding stars and gas. And just using the Doppler effect, they can infer the velocities and therefore measure a mass. And then for active galactic nuclei, there are other techniques that people use to measure the mass of the black hole. But these dynamical measurements, as I've said before, have been done on roughly 100 galaxies so far. And then your other question, I think, was about galaxy collisions. Was that it? Oh, black hole collisions. So that's a big question on the gravitational wave event rate. So it's still an open question. You know, there are some simulations that predict that it would take more than a Hubble time for the supermassive black holes to collide, to actually merge, and that most of the collisions may not result in an actual black hole merger. That will eventually be answered by LISA, which is a space interferometer that can detect the low-frequency gravitational waves anticipated with supermassive black hole collisions. So it's not yet known. It's an active area of research what the gravitational wave event rates will be for such collisions.
I'm Bob Hershey. I am a member. Does it look like there's a continuous range in the masses of these black holes, or there's some sizes that are more popular than others?
That's a very good question, and there is a selection effect, of course, because the more massive the black hole, the easier it is to detect it. As I mentioned before, there is this black hole desert, which really probably arises because of the technical challenges in detecting the smaller intermediate mass black holes. But in the local galaxy, I think I showed the plot there. Galaxies with black holes on the order of 10,000 solar masses. There are just a few around there, but really like around 1 million solar masses, all the way up to 1 billion solar masses. As you know from M87 has a much more massive black hole than our Milky Way black hole. So they don't seem to be clumped in certain, but there is a clear selection effect that the more massive ones are the ones that are discovered. I should say that James Webb will put constraints on supermassive black holes at higher redshift and may actually put some constraints on formation theories of supermassive black holes in what it finds at the higher redshift regime.
Hi, hello, my name's Charlton David Lewis II. I'm a member. So my question, well, first of all, I really hope you get time on James Webb. Looking forward to that. So hope they accept your proposal whenever you send it in. So you presented a fantastic quandary question about how did we get supermassive black holes so early in the universe. And so my question to you is sort of tangential to what you're already looking at. What type of data or observations would you want to see to maybe shed some light on that mystery? In my own head, in my own world inside, I'd love to see a similar picture that we have for the microwave background radiation, but for primordial gravitational waves. So I sometimes wonder if that type of picture with Lisa, as you already described, might shed some light on this mystery of why we have supermassive black holes so early in the universe. So what data would you like to see if you made the funding decisions for observations and satellites, so on and so forth? Thank you.
Very, very good question. And if only I had that capability. But I think Lisa is going to be an incredible mission and a very essential mission because that will directly allow you to detect these supermassive black holes at high redshift. They will allow you to measure the masses of the black holes. So that will be a definitive, definitive test. But that's a challenging mission, and that's far away. I do think there are going to be some important clues that we will learn from James Webb, both in studying the local population of dwarf galaxies, where, as I mentioned, the work for which we got some time, and other teams have also gotten time to look for these intermediate mass black holes. But there are also going to be constraints on the higher redshift universe by trying to look for signs of these accreting supermassive black holes at higher redshift. But Lisa is going to be the answer to a lot of these questions.
I can take a question from text question from our Zoom participants. David Rabinowitz asks, do we know the distribution of elements in the region of population 3 quasars? Are there heavier elements indicating a history of supernovas?
Very good question. So by population 3 stars, that's one of the things James Webb is going to be looking at, the first generations of stars and galaxies. But we think that the first generations of stars are going to be made up primarily of hydrogen and helium. And they're made out of pristine material. So prior to stellar nucleosynthesis in previous generations of stars, so they should be very metal poor. They shouldn't have significant contribution from elements other than mostly hydrogen and helium.
We have a question from Carl Merrill.
Thank you for that talk. One question I have is that most things in the universe rotate. So these are, I guess they call them curved black holes. And the question is, what speed, does the speed of the rotation of these massive black holes affect the spectrum that you see? And does it make any difference whether it's rotating one way or the other way? So that's the question I have. Right.
Yeah, that's an excellent question. And indeed, you would expect that the black hole would be rotating because the black hole grows over cosmic time, and as matter falls towards the center, the black hole should spin up, just like a figure skater when they take their arms in, spins up. And yes, indeed, the accretion, the inner disk of the accretion disk actually gets closer to the black hole, and you do indeed would expect a different signature from a rotating black hole compared to a non-rotating black hole. So yes, you would see a different signature.
Before we go to Cameo with the red microphone, I would like to read a comment that came in from Tony Tether, a former head of DARPA. He says, no question, I've had probably thousands of people brief me on the most arcane subjects, but none explain them as well as Shobita did on this one. So, high praise indeed. Question from the red microphone back there?
Wonderful. Can you hear me? Excellent. We've got a question from our YouTube channel from membership unknown, Thomas. Are the gases expelled from the interior of a black hole, or does it come from near the black hole?
Yes, that's an excellent question. And no, it doesn't come from inside the black hole. And we don't actually know the mechanism by which these outflows are generated, or these extremely energetic charged particles. And I should say that I think if you remember, I showed an image of a jet being emitted from the center of a galaxy. The energy in those jets can be equivalent to 20 billion supernova going off at once. So they're extremely energetic. They're moving at relativistic speeds, emitting what's called synchrotron radiation. And the actual mechanism by which they are launched and accelerated over such huge cosmic distances, 1 million light years, is unknown, actually. So that's one of the outstanding questions that people are trying to study. In fact, the EHT team is trying to study the jet launching in M87, and you probably heard about that during that talk. So it's a big mystery and pretty amazing what impact the supermassive black hole has. Yeah, another really interesting thing is that, as I mentioned, that this material is flung out at these relativistic tremendous speeds. And the amount of matter that you have outside of galaxies can exceed what's inside galaxies. And you actually find heavy elements way out in intergalactic space that can only be produced in stellar nucleosynthesis in the cores of stars. So it's pretty amazing what these black holes seem to be capable of doing, and they definitely have. They're not as quiet as one would think.
Michael Hammerschlag. I'm a journalist, and I've done things on space and various. I worked on Mauna Kea for a while on one of the telescopes. With the supermassive black holes, the billion solar mass ones, how many of those are there, and what do they have in common? Are they all like billions of light years away, or are they localized in any particular direction, or and what's your wildest idea on how they form?
Very good question.
And just answered so.
Oh, okay. So I told the story about quasars in my talk, and actually that's where the story of supermassive black holes began. We didn't know what was in the center of our galaxy at that time. That was in the late 1950s and early 1960s. In fact, it made the cover of Times. So if you're in journalism, quasars made it to the cover of Time magazine in 1963 or 64. I can't remember exactly. But basically, at that time, they were discovered in the radio part of the electromagnetic spectrum. And now there are 4 million known. So there are roughly 4 million quasars that are known. And I showed you that there's some that are being found at very, very high redshift when the universe was just a few 100 million years old. In terms of the closest one, the closest active or feeding black hole, if you will, is, I have to do the conversion in units that makes sense here. So roughly 10 million light years, which is close. Just to give you a sense of the scale of the universe, that is a relatively close galaxy.
My name is Scott Matthews, and I'm a member. So my question relates to the intermediate black holes in the dwarf galaxies. Mm-hmm. So you showed a picture of a dwarf galaxy with a red dot, saying that that was the sphere of influence of the intermediate mass black hole. But what I'm wondering is that at the center of the galaxy? Is the galaxy organizing itself around the intermediate mass black hole the way a larger galaxy would organize itself around a supermassive black hole? And if the sphere of influence of the dwarf galaxy or of the intermediate black hole is just the size of the red dot, then why is the galaxy organized around
That's a very interesting question. So the first question about intermediate mass black holes in dwarf galaxies, there are simulations that suggest that they may not be found in the centers of galaxies. In fact, there are simulations that suggest that 50% of them would be ejected out and somehow orbiting. And there are some preliminary observations by people that seem to suggest that that might be the case, but that's not definitively confirmed. Some dwarf galaxies don't even have a clear center. They're very irregular looking. So it's hard to say, is it organized into the center? We don't yet know. And as I pointed out in my talk, it's really an unknown area of research. It's not just my group that's working on it. It's really a cottage industry of people looking in dwarf galaxies, trying to find the black holes. And the vast majority of galaxies are dwarf galaxies. So even in our local group, of which the Milky Way is a part, I think it's something like greater than 80% of all the galaxies are dwarf galaxies. It's just Andromeda and the Milky Way is the big galaxies, but most galaxies are dwarf galaxies. And then the question about why is it sitting in the center? Somehow it's in the center of the potential well, but we really don't know the answers to these questions. Why is it there? How did it form? None of these questions are known.
Hi, my name is Laker, and I'm a guest of a member. Thank you so much for your fascinating talk. You mentioned that there's a limit to the rate at which a black hole can grow, and I would be curious if you could elaborate more on what that limit is due to the radiation pressure, and more how the radiation pressure causes the limit to come into effect.
Okay, a very excellent question. So this limit is called the Eddington limit. And of course, to have a gravitationally bound object, the force of gravity needs to exceed any outward force. So even in a star, there's thermal pressure that would cause it to, that counteracts gravity. So when material falls on a black hole, it radiates. And radiation, you can think of photons. they carry pressure. And so that is an outward force that counteracts gravity. So in order to have any object be gravitationally bound, the inward force of gravity has to exceed the outward force. And so if you have material that is radiating as it loses gravitational potential energy, heats up and radiates, there comes a point where radiation pressure would exceed the inward force of gravity, and that's called the Eddington limit. So there are some fancy ways that you can engineer it so that you can have super Eddington accretion, but in general that's difficult to do. So most accreting black holes in our local universe are radiating at significantly less than the Eddington rate. So it's challenging to have a black hole feasting and radiating and getting too luminous and exceeding this Eddington limit. Does that make sense?
Yeah, you also add the time scale so it's blowing up the time scale, making it harder for the black hole to feast and grow really quickly. So is this on the order of hundreds of millions of years that it's slowed down, or how does that work?
Yeah, that's an excellent question. First of all, I should say people don't realize that gravitational potential energy is extremely efficient. So black hole radiation from accretion disks on black holes is extremely efficient, much more efficient than nuclear fusion in terms of E equals mc squared. So in fact, to produce a quasar, you actually need to feed it only 1 or 2 times the mass of a sun per year in order to produce the tremendous luminosities that are observed from quasars. So it's an extremely efficient way of converting matter into energy, much more efficient than nuclear fusion. Sorry, I got sidetracked there. I forgot what your question was.
What's the time scale?
Oh, the time scale. So that's a good question. I don't think there are necessarily good constraints on that. We know that there was a period where supermassive black holes were extremely active at higher redshifts, and that most of the supermassive black holes in our local universe are not actively accreting. So we think, as I mentioned, that when the universe was younger, it was smaller, and we think that there were more galaxy collisions. And we think that galaxy collisions are where supermassive black holes grow, as I mentioned in my talk. And so we think that in the early universe, galaxies collided, and that's when most of the supermassive black hole growth occurred. And now it's more quiescent.
Shahid Aslam, a member of the Society. This was a fascinating talk. I want to ask you about a question that you teased us on. You said that JWST would not be able to look far back in time in order to see the seeding of these black holes. What technology improvements do you think should be made in order for the next generation of space telescopes to get us to look further back in time? Is it only just the sensitivity of the instrumentation?
Yeah, so that's a really good question, and one where I talked a little bit about LISA, because I think that is going to be the definitive test. Because
You might mention what LISA is.
Oh, okay. So you've all heard about LIGO. LIGO has, I think it's a 4-kilometer interferometric arm, and it's detected black holes that, as I mentioned before, the black hole merger with the greatest mass is 140 or so times the mass of the sun. So these are much smaller mass black holes. And the reason it can't detect the supermassive black holes is because supermassive black holes will give rise to lower frequency gravitational waves when they collide. And in order to detect these lower frequency gravitational waves, you have to have a much bigger interferometer. So I think the LISA mission, the I think it's 2 million kilometers versus 4 kilometers.
It's
So
space-based.
it's a space-based interferometer that hopefully will be launched in our lifetime. But yeah, I would say that that's going to revolutionize the field.
Yeah, just to clarify, it's a laser interferometer in space. It's been proposed. It's going to be done by ESA.
Yes.
And the U.S. had a program, but we decided not to do it. But they have a experimental small-scale set of satellites now in orbit, and so far that's proven the concept to work pretty well. So sort of audacious, but it looks like it probably will work.
Yep, so I have another question. David Lewis again. So as physicists, sometimes we get to verge on the philosophical. So I have a question along those lines. So it seems every time that we make a discovery of which we think is rare, it becomes common. So the Hubble Deep Field, LIGO as well, we found one merger and all of a sudden we see a bunch of other mergers. So with the observations that your team has made with AGNs and, a triple merger, which is just really awesome, let's assume everything your team theorizes is widely successful and true. What does that mean for our universe?
Yeah, everything exists. We just have to find it. Yeah, that's an interesting question. I'm not sure about those canals on Mars, though, that I started with.
You can be sure of one thing, it's full of mysteries.
This is true.
I'm going to ask about timescales, but I want to ask about one of the answers to your puzzle is that supermassive black holes are formed very fast and get old very fast. And the little guys you're seeing are just stars making little guys, but they've got nothing much to do with the big mega to billion solar mass black holes. So I want to probe at the lower. What's the shortest time scale you think? You talked about the Eddington limit. We're going back at the Z of 7. We're going back to a few hundred million years from after the Big Bang. Tell me, can I go back to 1 million or 10 million and can I be making these black holes? What is too short? 300,000 years, the surface is less scattering. We're probably not making them then. So, but give me a time scale ballpark so I can figure out what kind of Z we need to get to and what kind of time scale would.
Oh, so sense. You mean that if you have Eddington, growth at the Eddington limit.
And you have multiple collisions. We know that the length scale for galaxies is relatively about the same size as the distance between them. So we expect a lot of collisions. And you've made the very good sound argument that black holes are connected to the way galaxies are formed and grow. So what if you just make these supermassive black holes as you're first putting your galaxies together?
Uh-huh.
And what is the formation? I don't have a good time scale feeling for how long does it take to build a dwarf galaxy. Can you do it in 1 million years, I guess is another way to put it, if I want to be blunt.
That's a really good question. And I mean, the first point that you made on how much time do you need, we are already having a problem with that, as I mentioned in the beginning, because the highest redshift quasars are found at redshifts greater than 7. So, that's, as I said, a few hundred, and, I think the 600 to 700, when the universe was 600 to 700 million years old, you already had, and I think there's a new one that's going to be announced soon, that's close to 1 billion times the mass of the sun. And that already is placing constraints on the size of the original seeds. I mean, presumably, although there are theories of primordial black holes forming in the early universe, presumably you needed to have the initial stars formed before you could form a supermassive black hole. It's unclear whether you had the first galaxies, but, I mean, you can imagine that it's very difficult to suddenly have a gas cloud that becomes a black hole. You have to somehow get matter, to very high densities to form a supermassive black hole, and it's very natural to think that you could do that in the cores of stars. But it's not easy to think how you can form it, just in a gas cloud in the early universe. And so there are these theories, but they're challenging. So there are already constraints that make the theory challenging, I guess is the bottom line, that you already have these very massive black holes. Yeah, and I should say your point about could it be that the quasars are just these monsters that are really massive and not like the ones? That's actually not true, because we know, the EHT, the M87 black hole is, what is it, 6.5 billion? So it's a very massive black hole, an M87, and in many of the local galaxies, they're massive black holes. They're just not actively accreting. And even though I told you that there are 4 million quasars or so that have been discovered, the space density of quasars is really small. So they're in the local universe, supermassive black holes appear to be ubiquitous and in every galaxy. We're only detecting the really luminous things at high redshift that we call quasars, but they're still, in terms of space density, rare. Yeah, we just don't know.
The primordial, the one, delta T over T about 1 and part in 10 to the 6th, the primordial fluctuations in the CMBR, there's a lot of mass in them, but they're really big. They couldn't make these supermassive black holes. They make the super clusters of galaxies, right?
Yeah.
You couldn't ask them to be making a primordial slew of supermassive black holes, I don't think. They're too big.
I don't think so. You have to have, baryonic matter that is somehow, forming and where gravity can take over and form the black hole.
So can I sneak in a question or two here? So one question is this: I think and these may be naive questions because I'm not an astronomer or cosmologist. I'm a molecular biologist, mostly. First, you showed that there's a relationship between the size of the galaxy and the size of the black hole, I think.
Yeah.
And you suggested that suggests that the black holes are influencing or informing the formation of the galaxy. So I'm wondering why it isn't the other way around, that the black holes scale with the size of the galaxy because there's more matter in the galaxy for them to interact with and kind of accrete, for lack of a better word.
That's a really good question. But I think the size scale is important here. And I was trying to convey how tiny the black hole is and its sphere of influence compared to the size of the entire galaxy. As I said, like the Milky Way's black hole is only 7 times the radius of the sun, compared to 100,000 light years at the size of the galaxy. The actual matter that accretes onto the black hole has to get very close to the black hole, and it has to lose angular momentum. The matter that's way out somewhere in the outskirts of a galaxy really has no knowledge of the black hole at the center. It's just going on its happy journey, orbiting the center of the Milky Way without knowing that there's a supermassive black hole.
The other question is, so dark matter is kind of discovered because of the rotational properties that were measured. And you've shown that the mass of the black hole is calculated from the rotation of the galaxy, stars around the center. Is there any indication, any anomalies in the data that suggests that there's some involvement of dark matter? And is it possible that the estimate of the mass of the black hole is off because it doesn't take account of dark matter?
Yeah, that's a really good question. And I'm probably not the best person to answer that question. But my understanding is that there isn't, an impact on those small scales. on much larger scales, of course, dark matter dominates the motion of stars and gas in our galaxy. But yeah, so I would say on larger scales, obviously, it's an influence.
Blue microphone.
Scott Matthews again, and I'm still a member. We talked about using the IR to make some of these observations because it helps you see through the dust and interstellar debris and that sort of thing. And then the pictures that you showed, like the triple one, that's in the X-rays, right? And you showed a graph showing that you thought that the intermediate mass black holes, if they're accreting, are going to have spectral signatures at higher energy. And so what I'm wondering is, what about the blue? What about the ultraviolet? What about soft X-rays? It seems like IR is sort of at one end of the spectrum, no pun intended, and X-ray at the other. Are there observations being done in the middle somewhere? And are there regions in the middle where you would expect to get some good information?
Yeah, that's an excellent question. So the optical and the UV is even more significantly affected by obscuration, by dust. The other thing I didn't explain well is that the unique signatures happen to arise from spectral transitions that occur in the infrared part of the electromagnetic spectrum. So it just so happens that those emission lines are very strong and happen to be in the wavelength regime that James Webb is sensitive to. But there are some spectral signatures in the optical and UV part of the spectrum, but they actually are intrinsically fainter, and they are also affected by obscuration. So we think that in terms of the spectral signatures, we think that Webb is going to be ideal to search for the unique spectral signatures from accreting intermediate mass black holes, where previous methods have failed so far. Fingers crossed. Our observations are scheduled for July of next year. So we have 11 hours to point at those tiny galaxies. and yeah, keep your fingers crossed. Maybe we'll find that 1,000 solar mass black hole.
I think that's a really good place to end tonight's talk. So thank you so much.
Thank you.
Thank you so much.
Thank you, Larry.
And before we retire to the social hour, the next meeting will be number 2463 on September 9th, and it will start the 2022-23 fall lecture series. The speaker will be Drew Weissman of the University of Pennsylvania. Drew and his colleague in Germany were instrumental in developing methods for modifying RNAs that allows them to persist and is the basis for the current Moderna and Pfizer vaccines that probably everybody in this room has had administered to them. And this talk will be about the development of mRNA vaccines. So I think that should be very interesting to all of us. Keep checking the PSW website, www.pswscience.org, for updates as we put together the fall lecture series over the summer. Before we go, let's thank our volunteers. This list is probably wrong, but in any case, let's just thank our volunteers and leave it at that. So thank you all for being here and for doing this. And if there's anyone in the audience who feels like they would really like to help out with this stuff, please let me know, because we could use a few more hands. With that, I will accept a motion to adjourn the 2461st meeting of the Society. Do I have a motion to adjourn to the social hour? Second. All right, I think it's probably unanimous. Any objections? Meeting is adjourned.